Alright, to answer the second problem of the midterm redo, what we do is we have this circuit right here, and we're asked to find for an input waveform of 5 sine omega t represented right here at this terminal. We are asked to find and graph the output waveform of V out for this terminal right here when VD naught is equal to 0.7. So, examining the graph, we see that we have two diodes, D1 and D2, and we want to know how that affects V out. So what I did was I did an initial KVL where I considered that both diodes were on and performed an inner loop going through D1, D2, VI, and ground. And I pretty much came to the conclusion that this will only ever happen for a very technical instant when VI is equal to 0, which simulates them both being at ground and would pretty much cancel the diode's voltages to cancel out in the KVL. So basically, what I then did is I had to consider all the other values of the input waveform, which pretty much meant anything greater than 0 and less than 0. So for the case when VI was greater than 0, since VD1 is equal to 0.7 minus VI, this means that for all values greater than 0, there is not a significant voltage difference to cause VD1 to conduct and will be off. However, since the KVL of the loop from 15 volts to ground must be satisfied, and that means the D2 is going to be on, causing V out to be VD2 plus VR, which we know is a constant 1 volt because we have the 1 milliamp going through 1000 kilo ohm resistor. So that's going to give us a V output of 1.7 volts for all values of the input waveform that are greater than 0. So the second case we have to deal with is when VI is less than 0 volts. And this will cause the D1 diode to conduct as the voltage across D1 is going to be greater than 0.7 when VI is less than 0. That should be a less than. Because VD1 is equal to 0.7 volts due to D2 being on, or D1 positive terminal, due to the requirement of this KVL loop, this one is always going to be at a 0.7 voltage difference relative to ground. So what that means is that when VI is less than 0, it's going to cause this one to conduct, which is going to cause this V8 node to pretty much be VI plus 0.7. So then if that's going to allow us to pretty much do a KVL going from VI to V out, which is represented by this equation right here, which is pretty much the input waveform plus 1.7 volts, which we get from adding the voltage going through D1 and then the voltage gain through VR going to V out. So based on those two KVL equations, what we have is when we input in the most negative value, which is -5 for our input waveform for when VI is less than 0, we get that V output is going to have a negative peak value of 3.3 volts and a positive peak value of 1.7 volts. So if we add all this information together here in this graph, we can see that it is going to look something like where it's going to flatten out, maybe a constant 1.7 volts for when VI is greater than 0 volts, and the second it isn't, it's going to switch to the V out is equal to VI plus 1.7 volts, where it's going to start at 1.7, but then since VI is going to be negative, it's going to slowly become more and more negative, reaching that negative peak value of -3.3, and then coming back up until eventually repeats the cycle over and over as time goes on.